1013. Email. These are my coordinates. And I'm trying to find a grader for the course. I haven't found a grader yet. When I have the grader, I'll let you know. So we meet here, and if this blackboard is not large enough, maybe I can find a classroom with a blackboard that is larger. Actually, I requested 260 or 060, but then they give me this smaller classroom. Because I did not request any technology to come with the course. I usually use Blackboard. And all the classrooms with technology, I guess they want to reserve them for somebody else. Okay? So this is a course on waves and fields. In homogeneous media. But it's mainly electromagnetics. Okay, so because you can have all kinds of waves and fields in this world, but what I will cover in this course is mainly electromagnetics. So we always start with Maxwell's equations. So the first two lectures are pretty introductory. You might have heard materials of these two lectures from my previous classes. Okay, but maybe it doesn't hurt to hear them again, because some of these things are fun to learn about anyhow. Okay. Maxwell's equation, if I remember, it looks something like this: curl of P minus dv dt, curl of H is dv dt plus J, and then divergence of P equal to 0, divergence of D equal to rho. Okay, these are the four Maxwell's equations. And the wonderful thing about these four equations is that it's valid from atomic length scale to galactic length scale. These equations are responsible for the propagation of radio waves from outer galaxies to us. But yet, these four equations are responsible for the electromagnetic forces that we see inside an atom, like the Coulomb interaction and so on. You can derive Coulomb's law from these four equations. And these four equations are classical. Okay, but if you go to the quantum version, that if you study quantum electrodynamics, these are the four equations that are important as well. So you can think of these four equations as being important classically as well as quantum mechanically. So they are important equations in many respects, and they are to stay with us for many years to come. Okay, so you can have QED, classical EM, classical EM, you can have quantum EM or quantum electrodynamics. They are also based on these four equations. Okay, and what is more wonderful is that these four equations are relativistically correct. In the sense that it doesn't matter what inertial frame or inertial reference frame you are, these four equations are going to look the same according to Einstein's special theory of relativity. If you go to a different inertial frame, you will have to have different kinds of laws, but these four equations remain the same no matter. Say if you're in a spaceship that travels close to the speed of light, okay, and in that spaceship, these four equations remain the same. Okay, it doesn't matter how fast you are traveling. And what is more wonderful is that these four equations also inspire other kinds of more general theory, like if you probably might have heard of Yang-Mills theory. Yang-Mills theory is usually regarded as a generalized form of electromagnetic theory. Okay, it's based on differential geometry. So if you like to explore further, you can study this thing which are kind of an extension of this in the mathematical realm. And then you can go and study lots of other deep mathematics in order to understand what Young-Mills theory is, but there's something that I know very little about. Okay, it's something very deep in physics, but it's something that I know very little about. And if you like further, you can also study quantum electrodynamics. Of course, this equation gives rise to hosts of applications. Host of applications because they are very important in electrical engineering. I would regard electromagnetics as one of the very important key technologies for high technology. So if you want to study high tech, you have to understand the electromagnetic theory well. And more recently, what is amazing is that because of the nanofabrication technology, because of nanofabrication technology, we can make things on the order of 10 nanometers. And if you look at blue light is about 400 nanometers. Okay. So we can make things that are much shorter than the wavelength of light now. And that makes things quite different, and that gives rise to a new field called nano-optics. Nano-optics is an interesting emerging field, but Maxwell's equations still hold true in nano-optics, even though the length scale is very, very small. Length scale is on the order of nanometers, but you still have to solve Maxwell's equations. And because of the emergence of nano-optics, people are solving Maxwell's equations more seriously in the optical regime. In the beginning, you probably know that optics was mainly something to do with ray optics. Because things are so large compared to wavelength that you can essentially simplify things by ray. You can understand how lens work by just ray tracing. Okay, and you can design a lot of optical elements by just using ray tracing. But this was the time when optical elements are much larger than wavelength. But now things are different. Optical elements can be sub-wavelengths, they have nanoparticles. You have nano-optics, nano-antennas. You can have even things like nano-MEMS, nano electromechanical systems. I guess this stands for nano electromechanical systems. You can have lots of wonderful things happen in the nano dimensions. Nano implants. Nano implants. They can put inside the human body. And they are even thinking of making things that are much smaller than your size of your blood vein. And then manipulate these nano implants around using electromagnetic forces. And then you can move these small gadgets around your arteries of your vein, maybe to find new cures for new diseases. So there are lots of emerging technology that are related to Maxwell's equations, and you still have to solve these four equations. As I said before, these four equations are valid down to atomic length scale. So what else can we think of? Nano implants, plenty of things. Okay, Casimir force. A force that was not that important and has been proposed to exist for many years, but it was not until 1997 experimentally verified. And it was experimentally verified because it is a force that happens at extremely small dimensions. If you have two pieces of metal that are separated by nano dimensions, then there is a strange kind of force between the two objects. And it was proposed to be there, but not measured or confirmed. But recently, because of nanofabrication technology, you can make very, very small things. You can actually confirm that this force is actually there. And so it opens up new fields for interesting things. So one of the things that is very interesting is that a lot of things that were actually done in microwaves are now being repeated in optics, in nano dimensions. Things like optical coherence tomography. You probably heard of this thing before. This is, in my opinion, the same physics as ground penetrating radar. And also subsurface seismic. In ground penetrating radar and subsurface seismic, you send a wave into the ground and listen for echoes. And by listening to those echoes, you try to infer what the profile of the Earth is, electromagnetic profile or elastomagnetic mechanic profile. But in optical frequency, this is a lot harder to do because the wavelengths are a lot shorter. But then this friend of mine, Jim Fukimoto, okay, he actually was successfully, he did this at MIT, and he was the first guy to do it using optical frequency, and he became very famous, okay, for being able to do this experiment at optical frequencies by sending light pulses into the human eye, and then looking for echoes, and then using coherence interferometric measurement to figure out what those echoes should be, and from that you can infer what the profile of the human tissue should be. And there are things like optical imaging, and then things like interferometric imaging, Okay, lots of things that actually happened at microwave before, like interferometric radar, synthetic aperture radar. It's now been repeated in optics, so that you can get 3D images of the surface of a tissue. Interferometric SAR, or synthetic aperture radar, is used to find three-dimensional pictures of the Earth's surface from satellite remote sensing. Okay, but now this kind of technology has been repeated. And lots of things happen to be that way, like even in communication theory, wavelength division multiplexing, and a lot of those communication technology were first done at microwave, and now they're actually being done at optical frequencies. Okay. So Maxwell's equations are going to stay with us, and they're going to stay with us for a long time, because it's valid for all length scale, as technology advances, they're going to be with us. Okay? So let's go back to looking at this four equations again. So what does the curl of E mean? Curl of E. Curl is actually a measurement of rotation. Okay. When you take the curl of something, you actually measure what the rotation of the electric field is. In old notation, if you look at some old textbook, we still use this notation. Rotation of E. Okay. Of course, you also see this notation being used, curl of E. Okay. So curl of E is essentially that if you have an electric field, okay, it's defined to be the limit of E dot dl in the circle in the closed contour divided by the area of the contour going to 0. So take any E field. If you want to find its curl, this is the basic definition. You take the contour around this area and integrate this E field, perform this integration around this contour, and then shrink that contour to as small as possible, and then normalize by the area of this contour. And that is what the definition of the curl is. So it's quite clear that this thing will be non-zero if this integration is non-zero. Okay, so if this integration is non-zero, that means there's a net rotation, and so you can think of putting a paddle wheel in a fluid. A lot of this concept comes from fluid. So you can think of a paddle wheel, and then if the fluid has rotation, this paddle wheel will start to rotate. Okay, that's what curl is. So if curl of the E field is non-zero, that means it has rotational component. Okay. Divergence of D. What is the meaning of this? This says that you take a D and then dot with the normal and then do a surface integration over a closed surface and then normalize by the volume. If you take any small volume, the volume need not be cubic in shape, but take that electric flux D around this small volume and then perform a surface integration of the normal flux, normal component of D, and then normalize by the volume. That's the definition of what the divergence is. Okay? It is quite clear that if this surface integration is not zero, it means that there's a net flux oozing out from this region. In this picture, it's quite clear that this integration will not be zero because all the n dot d, if d is of this form, n dot d will not be negative. All of them will be positive, and there will be net flux leaving this place. So the divergence of d is a measure of how much flux is actually leaving a point in space. Okay, how much flux is leaving a point in space, and then of course then you can look at these other things, and they're like strange things. Okay, and Maxwell's contribution is actually to give rise to this term. Okay, and the first term is actually Faraday's law. The second term is Ampere's law, and also generalized Ampere's law. And the third term and fourth term, this one is actually coming from Coulomb's law, and this is Gauss' law, or something like that. Okay, so different people contributed to different parts of electromagnetic theory, but Maxwell gets the credit for it finally. But the person who wrote Maxwell's equations in this very nice form that we see presently is actually due to Oliver Heaviside. Oliver Heaviside was an eccentric electrical engineering genius. He discovered lots of electrical engineering things. And one of his contributions was to take Maxwell's equations written in its original form and wrote them in this very simplified form. Okay. So of course, in free space, we always say that in free space, we always say that B is equal to mu H, or maybe mu naught H, just to indicate that this is a free space parameter. D is epsilon naught E. Then Maxwell's equation simplifies, and then you can, of course, get this equation, and curl of H is equal to epsilon naught q e dt plus j and so on. And it's often said that mu naught is a sign. It's 4 pi times 10 to the minus 7, right? I think if I remember that correctly. Mu, did I get it correct? Okay, this is mu naught is assigned to be this value. Epsilon naught is equal to 8.854 times 10 to the minus 12. This is, I think, in terms of henries per meter. This is in terms of farads per meter. Okay, so why is epsilon measured, and then why is mu naught assigned? Okay, why is it that we can assign mu naught to be something, and then we have to determine epsilon naught by measuring the speed of light? Essentially, if you have a simplified Maxwell's equation that I write in this form, E is equal to minus mu naught dH dt dx, H is equal to epsilon naught dE dt. Say I have this simplified Maxwell's equation in one dimension and so on. And I can always redefine my mu naught. Say if I can define mu naught prime to be mu naught over A, right? And then I can now rewrite this equation as dE dx is equal to minus mu naught prime dH times A over dt. And then if I do that, then I can always write the second equation as dHA plus epsilon A dE dt. So if I can always redefine my constant in those two equations by, say, defining a mu naught prime. If I do that, then I put a mu naught in the denominator, A in the denominator, and put an A there, the second equation, and multiply by A again. So my two constants change. Okay, so I can always redefine my constants. Okay, essentially I can always redefine my constants in these two equations, but if I want to study something that's invariant, then I take the second derivative of this equation. I get this equation, and then from the second equation, I get this equation. D squared. Yeah, I think this should be a plus sign, otherwise I won't get the wave equation back. Okay, plus sign. Okay, then I have this wave equation back. You probably have learned this as a wave equation. Okay, and it says that this equation has a velocity v, which is given by square root of mu naught epsilon naught. And this velocity can be measured. So it's a product of mu naught and epsilon naught that can be measured, and that determines the velocity of the propagation of this set of equations. You can change the constant in whichever way that you like, okay, in the beginning of Maxwell's equations, but the velocity of light is not going to change. And hence, this product is not going to change. If you change to a new constant, this product is not going to change, okay? So that's why we can assign mu naught to be a certain value, and then get the second value from measurement of the speed of light. So actually, epsilon naught is proposed to be tagged to the speed of light, and that the speed of light is determined to be precisely this value as an integer number. if we determine the speed of light to be precisely that number, and that can be used to determine the epsilon naught actually. Okay. And so that is somewhat determined by measurement, and the length of meter, I presume, is also determined by this number over here. Okay, the length of meter is also determined by that number over here. Okay. So we start with Maxwell's equations that I have just erased, unfortunately. But we usually like to write them in time harmonic form. And usually we say that E of RT is the real part of a complex vector, E of R and e to the minus I omega t. I will use this time convention in this course that is usually used by people in optics. Okay, that we use e to the minus I omega t, and in microwave and circuits, people like to use this time convention. So you just change I to minus j. Okay, when you don't like I, you just change I to minus j. But in this course, I will use e to the minus I omega t time convention. Okay, and this is called a phasor notation. So given any time harmonic function can always be written in this manner. I will call this a poor man's Fourier transform. What it says is that any time derivative of E now can be written as in the phasor wall. If I differentiate this with respect to t, I get this representation. So in the phasor wall, any time derivative becomes minus I omega. And you get the same effect, okay, by doing Fourier transform. And in some textbooks, they will not use this phasor notation to get or to arrive at a new set of Maxwell's equations. Okay, and then you have this other set as well, and then you have this other set as well. Okay. In some textbooks, they will show how to get to this point by using Fourier transform. Okay, I can actually denote this more explicitly as phasor quantities now by using an unbuilt Theodore. You can also get here by Fourier transform. That is starting out with Maxwell's equations and assuming that any field quantity that I have can be written in terms of if I write all field quantities that I have in this manner, plug them into Maxwell's equations, we'll get the same result that I have here. You think of this as either phasor quantity or Fourier transform quantities. They're the same thing. Okay. And as you can see, Maxwell's equations are not complete until you add in the constitutive relationship. Because you can show that the third and the fourth equations are usually derivable. If omega is not 0, if omega is not equal to 0, I can take the divergence of the first equation, divergence of the curl of E is equal to 0, is equal to I omega divergence of B. So this implies that divergence of B is equal to 0. So you can see that the third equation is derivable from the first. Similarly, I can take the divergence of the second equation. I will get 0 on the left-hand side is equal to I omega divergence of B. plus divergence of J. And I am supposed to get the last equation by taking the divergence of this equation. What equation do I have to invoke in order to get the last equation? Do you know? Charge continuity, right? We have this important equation. Divergence of J is equal to this in the time domain. In the phasor world, it will be this equal to I omega rho. And if you invoke this, you'll get this being equal to I omega rho tilde, and then you get the last equation. So if omega is not equal to 0, we don't need the two last equations. You only need the two last equations when omega is identically equal to 0. So in electrostatic and electrostatic, we need to solve all the four equations. But in electrodynamics, we need only to solve the first two equations. They are sufficient. Okay? So this is an abrupt jump. An abrupt jump in the sense that you solve equations very nicely for electrodynamics. But when you let the frequency drop to 0, you sometimes not necessarily get the equations of electrostatic and electrostatics, because you need these last two equations for electrostatic and electrostatic. Okay? Two equations are not derivable from the first two if omega is equal to 0. So this is a very complicated thing in the field of computational electromagnetics, in the sense that if you start to arrive at a solution for Maxwell's equations valid for non-zero frequencies, if you let the frequency drop to 0, the solution is not necessarily valid, because it did not take into account of the last two equations. Okay? So most of the time solving the first two equations is sufficient. Okay, but if you solve the two equations, this is usually known. Say you drive the system with some source, and this is known. Then you still have four unknowns. With two equations with four unknowns, that's not good enough. So you need more equations, and those are called the constitutive relationship. Constitutive relationship. Okay. And there are different kinds of constitutive relationships. And the most general kind can be written in this manner, not necessarily the most general, but a general form can be written in this manner. Okay, and then B is equal to mu dot H plus theta dot E. Okay, this is a very general form, and media with this kind of thing are called bi and isotropic media. Okay, that you allow the D to be coupled to the H, the B to be coupled to the E. Okay, bi and isotropic media, and then you can have somewhat a specialized form. And when a medium is describable in this manner, this is called an isotropic medium. Okay. And then you can have even the simpler form, which is usually the form that is more commonly observed, where epsilon becomes a scalar. Okay. In this form, the D flux need not necessarily point in the same direction as the E field. The D flux need not point in the same direction as the H field, but in this form, they point in the same direction, and we call this an isotropic mean. Okay. And then you can classify different kinds of media according to what epsilon and mu are. And if these things are functions of of position, then you call this an inhomogeneous medium. Okay. And then if this thing is a function of frequency, of course this itself could also be functions of frequency. This is called a frequency dispersive medium. What does frequency dispersive medium mean? When epsilon is a function of frequency and mu is a function of frequency, what does that mean to you? What does that mean? Ken, what does it mean to you? No? No meaning? What happens if epsilon and mu are not functions of frequency? What happens if they're constant? What does that mean to you? What is that? What do you say? Okay, there's one possibility. Same phase velocity for all frequencies. And what does that mean to you? Instantaneous response. Very good. If epsilon and mu are not functions of frequency, it means that whenever you apply, let's take the very simple case. Whenever you apply, say vacuum has that property. Whenever you apply an electric field, you instantaneously get the electric flux. Okay? That is what it means when this is independent of frequency. Because we went from the time domain to the Fourier domain, you can go from the time domain to the Fourier domain through the phasor or to the